Hello and welcome to the New York City Category Theory Seminar. Today we're having Astra Kolomatskaya.
Kolomatskaya, yep.
Kolomatskaya, the objective metatheory of simple type lambda calculus. Let her talk first, and then.
Hello, I'm Astra Kolomatskaya. I'm a student at Stony Brook University working with Emily Real. And today I'll be telling a story in 3 parts. So the first question is, what is lambda calculus? The second question is also, what is lambda calculus, but at a deeper level? And the third question is, how do I prove properties about lambda calculus? And really, these are the 3 parts of the story. So first off, we have to discuss what is lambda calculus in the first place. And so that's this section. And in math, we're familiar with functions. Now, functions sometimes we think of just as abstract relations. But sometimes we think of functions as being given by a formula. In our world, we'll think of functions as being defined by their formula, so more intentional than extensional. We could write f of x equals x squared, but then we're giving f a name. What if instead we didn't want to give a name? In math, we'd write x maps to x squared. In computer science, we'll write lambda x dot x squared. So lambda is known as an abstraction. This just says that this is the variable of a function, and the function's body is given following the dot. Now, one thing is, so how are we going to describe what lambda calculus is? And a good notion is syntactic, the notion of a grammar. So what are the natural numbers? A natural number is either the z or the successor of another natural number. And this can be compactly represented in the form n is z or s of n. This is a context-free grammar. And what does it tell you? For example, it tells you that s of s of s of z is a natural number. You can sort of think of these as building up trees, describing syntactic expressions. So with this notion of grammars, I can tell you what the language of lambda calculus is, defined syntactically. And how we're going to do it is there are going to be 3 syntactic categories of terms. The first is the category of a variable. Now, when I write x, I'm going to mean any of the infinitely many lowercase English letters. This is our collection of variables. And lambda is going to be written as lambda some variable dot some term. And what we're describing is the grammar of terms. The third variant is an application, a term being applied onto a term. And I can give you some examples of things that we can do with this. So the important thing to keep in mind is lambda calculus, 3 grammatical variables, 3 grammatical variants. Every single term is either a variable, an abstraction, or an application. So here's an example of a term, just a variable, the variable a. That's a variable. Variables are terms. Variables don't have to be bound. They don't have to have meaning. Here's an example, lambda x dot x. We think of this as the identity function, right? So we're abstracting over a variable, and then we're just returning that variable in the body of the function. Here's another example, lambda x dot a. This is the constant function. X and a differ. So this just returns the variable a no matter what you throw into the function. And here's another example, lambda s, lambda z, s of z. So how you think of this is, well, it's a function that sort of takes a function and then takes an argument and applies the function to the argument twice. And you can think of this somehow as being the number 2. You can sort of encode all numbers by how many times you apply a function to an argument, right?
Could you stand a little further to the left of the slide so you don't have your head in front of you?
Of course. Now, before I said this is the identity function. So what do I mean by the identity function? So where's the functional part of this? And that's that these terms actually have a meaning. In math, if we have the example that we started with before, f of x is x squared, then f of 3 is 3 squared. So there's a notion of the semantics of functions, and it's...
make my students understand.
Yeah, that's just understanding variables and bounding, and like this is actually a large part of what Calculus A is about. Getting students to just appreciate syntax and appreciate just manipulating formulas. So what's the meaning of a function when you apply it to an argument? Well, the idea is that you take the body of the function, you take every single free occurrence of that variable in that body, and you replace it with the arguments. And we can write this as t with x substituted with the term s. So this is a notion of reduction on lambda terms. And this is known as the beta law. The beta law simply says that when you evaluate a function on an argument, it reduces to the substitution of the argument for every occurrence of the free variable inside of the function's body.
So is that another term there? That thing on the left, lambda x dot t in brackets s?
So we're going to talk about this later, but the idea is that somehow substitution, more intuitively we understand what substitution is, right?
That's not a term.
It can be or it can't be, and that's going to be a point later. So one way that you can think about it is you can just define this recursively on terms. You can define what substitution is, right? Then this is just a definition of another simply typed lambda calculus term. In our grammar that I gave before, I did not have a syntactic constructor for substitutions. So I mean this as a recursively defined procedure. So here's an example. What this is it's a calculation that 2 plus 2 equals 4. How do you think about this? Well, what are natural numbers? Natural numbers are the definite answers to questions of the form, how many apples are there in this basket? So if you have 2 baskets, how do you count them? Well, first off, how do you count one basket? You start from 0, you remove apples, you increment your count. So you can count to any number starting from 0. If you have 2 baskets, well, you can combine them, but that's cheating. One way is you count one basket, then you start at that number instead of 0, and then you start counting up from there when you count the second basket. So that's what this term represents. It takes 2 numerals, then it takes a successor and then a 0 operation, and what it does is it takes one numeral, it gives it the successor function, and instead of 0, it gives it the other numeral at MSZ. So you count the M basket, and then you count the N basket starting at the count of the M basket. That's what this term represents, and this is 2 and 2. So if you look at this, what's going to happen is this is a function of 2 arguments, or rather a function that returns a function that takes an argument, and here we have these 2 arguments. So they're going to be substituted in for n and m inside of the function's body. Here was n, here was m, here is the expression. Now here, sz being evaluated at sz, so those just get plugged in. And so that reduces. And now you're plugging in s and sort of s of z inside of this expression. So z gets replaced with s of z, and you have lambda s, lambda z, s of s of z. So I did 2 steps in a row, and every single step here. But sort of doing it 2 steps in a row, we should remember that this is a 6-step calculation then. In 6 steps, we were able to reduce 2 plus 2 equals 4. And when I count 6, this will come up, be relevant at the very end of the talk. So what's the cool thing? Well, the final expressions, so that's a normal form. What do I mean by normal form? I mean that there are no instances of the application of an argument onto a function that's given by a lambda term. When you have that, you can reduce it, right? Because you have a function defined by a body, and then some variable, you can reduce it. So expressions that don't have any of these loci of reduction are called normal expressions. Or normal forms, rather.
And if you have 2, then you can localize both of them, or you can reduce both of them, no?
If you have like an application, then you can reduce the left-hand side and the right-hand side, right?
Right.
But then maybe the left-hand side will reduce to a lambda, and then it might go further, right?
Right.
So here's an example. This is called the term omega. You have a term, what it does is it takes something and it applies it to itself. We're living in a world where functions solipsistically act on functions. So everything's a function as far as we're concerned at the moment. And so what it's going to take is it's going to take something and apply it to itself. And what are we going to feed it? Itself. So what happens is this term gets replaced inside of the body of this term for both occurrences of x, and what does that reduce to? The very term itself, right? So after each reduction law, you make no progress. So no matter how many times you apply the beta law, you're not going to get down to a normal form. So a normalization theorem does not hold of this language, which is called untyped lambda calculus. And this is where we bring in the idea of what is type theory in the first place.
So this is why untyped type theory is not consistent, or what is it not?
So it's sort of, if you have non-terminating things, you do have like inconsistency because you can sort of return something of a certain type by just never returning it, right? So often when you have non-halting computations, you're able to sort of return things by just giving non-terminating computations, and that's like a cheating way of producing something of a value. So what does consistency mean? Consistency means that it's not the case that every type is inhabited. Well, we don't have types there, right? So we can't say what it means for untyped lambda calculus to be inconsistent because it's not a type theory. But in theories that actually have types, having non-terminating things would let you sort of populate and inhabit any type, which would be inconsistency.
It's like untyped set theory is, Russell showed that untyped set theory.
Exactly.
So this is like that. Okay, so we need types. I like that. Okay, good.
So what are we going to, before we even talk about type theory, let's just talk about logic. So what's logic? Let's talk about minimal logic with implications only. So what do we have? Well, we're going to have a bunch of uninterpreted propositions. And they're going to be represented by, again, the infinitely many capital letters in the English language. That's our infinite set of variables. Then what we can do is if we have, so all of these propositional variables are propositions. Also, if you have any two propositions, you can form the arrow between them. So if A is a proposition and B is a proposition, or rather T or NS are propositions, that suggests that they're compound, then T implies S is also a proposition. Now, as to how you actually read this, because how do you parse this? Is this A implies B implies A, or A implies B implies A? And the way that I said it, there was slight spacing of sound, although probably completely inaudible. So we say that arrows are going to be right associative. So this is A implies open paren, B implies A close paren, right? So now what we're going to do is we're going to say, okay, so that's just a syntax. We've defined syntactically a collection of propositions. Now, some propositions are more distinguished than others. For example, if you say A implies A, that should be a proposition that has a proof, right? Because anything should imply itself. Whereas if you just say A, where A is an interpreted proposition, well, how are you going to inhabit that, right? So somehow there's a difference. So we need a proof system. And in our proof system, we're going to have judgments. And judgments are going to be sequence. And sequence are going to be of the form gamma turnstile T. Where what is gamma? So this is where we're going to make the choice that's going to confine us to the notion of simple type theory as opposed to dependent type theory. Gamma is going to be a list of types. So it's just a collection of hypotheses. And from a collection of hypotheses, we say that something follows. So that's what the sequent represents.
So these,
And T is one type.
T is just one type, and gamma is going to be a list of types. Here, gamma is a list of assumptions, a context.
And are you going to get to dependent type theory?
Not in this talk, however, the research that's went into this talk, later I considered the dependent notion, and then ideas from there bled into what my current thesis project is.
And can you say what dependent type, how a context is different there?
Yes, I can. So the problem is that your notion of types isn't that there's just types defined by a grammar. The catch is that types are defined by what I call, personally in my research, a type structure. So it's not just, like, think about the following thing. N is a natural number, M is a natural number, P is a proof that N equals M. That sentence, N equals M, it only makes sense once you've said that N and M are natural numbers, right? So the natural numbers, blackboard N, that's a closed type, right? So imagine you have a context. You sort of extend by blackboard N, you'd extend by blackboard N, and then once you've extended twice, you have a new type available to you, little n equals little m. And sort of this co-inductive tree-like structure, that's what the types in dependent type theory look like. Whereas in simple type theory, they just look like a set of types.
A sequence, well, do you depend, is gamma a sequence or a set?
So it is actually a list, so it is ordered. Well, a sequence is infinite, whereas a list is finite.
And independent, it's a sequence, but with more structure, namely the structure of a tree.
Right. So instead of having a set where every element of the sequence is from a set, it's like a traversal down a tree. That's what dependent contexts look like.
If I add that McBride has a wonderful term for those, which we like to use, which is a telescope.
A telescope. Yes, exactly.
Because you can think of it sort of, each piece extends from the prior piece.
Oh, so that's the tree structure. It depends what one thing
Is that
depends on the other.
related to the telescopic limits in topology?
No.
Okay, so what's our proof system? Our proof system just has 3 rules. The first rule is the assumption rule. If you've assumed something, you know it's true, right? So what this says is, really this rule has no hypotheses. This isn't a hypothesis of the form of a sequence. It's like just meta-theoretic hypothesis that T is a type in your context gamma. So this is like list lookup if you were doing an implementation. But this rule has no hypotheses, morally speaking. There is no hypotheses that are sequence. Now, application introduction says that if in context gamma with t, you can prove S, then in context gamma without t, you can prove t implies S, right? And then the implication elimination is modus ponens. If you can prove t implies S and you can prove t, then you can prove S, right? So that's 3 rules. 3 rules defining minimal logic. Now, what can you do with these 3 rules? Well, the idea is that these 3 rules are going to be like tree constructors. I'm not going to write sort of context lookup. Suppose we want to prove something like A implies B implies A. So if you're given a proof of A and you're given a proof of B, then you can produce a proof of A, right? So how are we going to prove this? Well, here, we're going to abstract over A, we're going to abstract over B, and then we have a context in which we have A and B, and we want to prove A. And that follows by our assumptions, right? Now, here's a more interesting example that involves modus ponens. We have a proof of A, we have a proof of A implies B, we abstract over both of them. Then, since we have a proof of A and A implies B, we can use modus ponens to conclude B. So, when you actually read these trees, typically sometimes you want to read them from top to bottom, but I recommend reading them from bottom to top. Sort of, this is what you want to prove, and then you're applying operations to reduce it to things which eventually have no assumptions. So I really think these should be read from bottom to top.
The bottom line is right associative?
Yeah. So this is, if you have A and you have A implies B, then you have B. Whereas if it was associated the other way, then it would be you have a proof that's A implies B, whereas no, you have separately a proof of A and a proof of A implies B. So the arrow is right associative, you're right. That's just a convention that we're going to take. Awesome, so that's logic. Why am I talking about logic? I was just talking about lambda calculus. Well, what is the constructive interpretation of logic? So constructively, what is a proof of an implication? T implies S. So we can think of it as some construction that, given a proof of T, gives us a proof of S. Now, what do I mean by a proof of T? So what we're going to do is we're going to identify a type. Since I'm a homotopy type theorist, I'm going to say with the space of its proofs. Every proposition is the criterion of what it means to validate the proposition. That was, well, that was Howard's big thing, right? I think that's, yeah. Now, so what is a proof of T implies S?
This
Well,
is one of 2 ways to interpret type, isn't it? There's another way.
what's the other way?
Isn't there 2 fundamental ways to understand this? There's another way.
I'm not sure what exactly that's
Oh,
referring to.
That's the universe?
Maybe I'm thinking of something else. Like, how does type theory extend ordinary logic?
Right, so when we're thinking of it constructively, the problem is sort of like you have like double negation elimination, then you can sort of pull a proof from thin air. And then this interpretation of like functions which we can actually compute on becomes a bit more difficult. Although there are like type theories that sort
I'll
of
think of
model.
something else. Never
Yeah,
mind.
maybe. So anyway, what then is a proof of T implies S? If we were thinking of T and S identifying them as the space of proofs, then it's a function from the space of proofs of T to the space of proofs of S. So for example, if SF is a proof of T implies S, and A is a proof of T, then the application F of A should be a proof of S, right? But we already have a perfect language for discussing functions, don't we? So now we're going to combine the 2 things that we just did before and construct a type theory. So what we're going to do is we're going to construct simply type lambda calculus. We're going to combine lambda calculus with types. So we have a grammar for types. A type is a propositional variable or arrow type. And a term is either a variable, an abstraction, or an application. Now, in an abstraction, we're going to annotate the variable with its type. So we're changing the grammar a bit by giving type annotations on variables inside of abstractions. So sort of the category of propositional variables and of type variables, when they're lowercase letters or uppercase letters, so of course they're different, but we're going to assume that all of these things are distinct, and sort of the grammar for terms, the grammar of types, they live in separate worlds, which doesn't happen in dependent type theory. In dependent type theory, types mix with terms.
Don't you have to say what your lambda is, what type your lambda is?
So that's what we're about to discuss. So right now this is just a grammar, right? So the problem with this grammar is that you can say some meaningless things, right? And so the question is, what does it mean to be a meaningful lambda term, right? So by the way, the elements of the top grammar are known as types, and the elements of the bottom grammar are known as terms. So what connects the two of them, apart from variable annotations? So we're going to take the proof rules for minimal logic, and we're going to annotate them with proof terms. So now we're going to change our sequence. Sequence aren't just a context gamma implies t. It's now the assumptions in gamma prove t with proof little t, right? So now we're going to syntactically construct proofs for all of these things. And now what is a context? A context isn't just a list of assumptions. It's actually a list of variable bindings. So every assumption in the context is going to have a variable assigned to it. Not an arbitrary term, just a variable.
A variable or a type?
So a syntactic variable within the term grammar, the context is going to say like little x is type capital T. Little y is type capital S. So I'll give an example in a second. So how are we going to annotate the proof rules? Well, so for example, modus ponens, if f is a proof of t implies s and a is a proof of t, then what syntactically should represent the proof of the thing? As I motivated before, it's function application, so we're going to use application. Now, what about this example? If t, little t, proves s in context gamma with the added assumption t, which is bound to variable x, then you can abstract over this. So abstraction exactly represents this rule. And variables exactly just represent context lookup. So notice, by the way, 3 proof rules in minimal logic, 3 syntactic categories of lambda terms. This tells you, you can read now, rethink about this. This is a proof rule for how you type an application. In order to type an application, you type the function and then you type the arguments. This is how you type a lambda term. You remove the binder and then you type the body within a context in which you've given meaning to x, right? And then how do you type a variable? Well, in order to type a variable, you need to know what the variable's type is. It needs to be bound, right? So free variables aren't acceptable now. If you have a free unbound variable and it's not bound by your context, then you don't know what its type is and it's not a meaningful expression. Does that make sense? So I'm about to show you how the proof trees that we looked at before, maybe I'll do the slide first, get represented as lambda terms. So here now, sort of the proof of, in the empty context of A implies B implies B. What we're going to do is we're going to first abstract over a proof of A, we're going to abstract over a proof of A implies B, and then we're going to take that function and apply the argument A to it. Think about this just in function land. We want to produce something living in the space B. We're given an element in the space A, and we're given a function from A to B, right? How do we get an element in space B? We apply the argument to the function, right? So this entire proof tree, it's actually contained in this proof term, because this proof tree is uniquely reconstructed from this term, because at every single typing stage, here we're typing a abstraction, so we have to use implication introduction. Here we're typing an application, so we have to use implication elimination. Here we're typing a variable, so we have to use the variable rule, right? So you see that in fact this big proof tree, we don't need this big proof tree, we just need this proof term. And so what are the meta-theoretic properties of this? Well, the meta-theoretic properties are that every term has a unique type. Every well-typed term. So what is a well-typed term? A well-typed term is a term that has a valid sequent. In the empty context, t has type, little t has type capital T. So if there is a sequent that can be derived, then the term is known as well-typed. So every well-typed term has a unique type. There aren't 2 types that a term can have. And that's because we basically have annotations on the lambda. If you consider the function lambda xx, that's the identity function on anything. But if you add a binder to a type binder to what x is, then you can uniquely reconstruct the type. Now, every single well-typed term has a unique typing derivation, because your rule that you're applying at every point is forced. Every minimal logic derivation corresponds to a unique proof term. And what the best thing is that this entire process, you can write an algorithm to do it. That's known as type checking. It's basically linear in complexity. You just traverse the proof tree. And computation preserves types. That's a very important property.
Minimal logic derivation, minimal with respect to which order?
The proof system that I described before is called minimal logic, with 3 rules.
Oh, sure. Okay, that makes sense.
One second. Can you explain to me why, the whole purpose of this was to make sure you don't get the inconsistency of untyped lambda cascade?
Yes.
Can you show me why that doubling function can't be done this way?
Yes, I can. Well, I'm going to rip the main results. So there is a theorem. The theorem is known as normalization. And it says that every well-typed term reduces to a normal form in a finite number of steps. So if we accept this theorem, which is basically what I'm going to be talking about, if you think about a type theory, the meta-theoretic Gold's theorem is normalization. That implies consistency. Because why? Because you have a type of normal forms. You can prove that not every single type is inhabited by doing induction on the normal forms, right? That's the catch. So if we have a normalization theorem, then sort of a meta-theoretic corollary of this is that this term is not well typed for any possible variable annotations because it's not normalizing, right? Now, if you actually, for me, the normalization theorem implies that this term isn't well typed. Now, why do we have a normalization theorem? And how would one establish a normalization theorem, right? That's the question. So this finishes part 1 of 3 of the talk.
What do you mean if it's true? Is it true or not?
It is true.
Okay.
When I say it's true, I mean I have written this proof up in a proof assistance in a very special way. So if we believe in proof assistance, we have this theorem.
I think the if it's true is also saying, well, we've got one logic presented here in one type system.
Right.
But you can do the same setup for many type systems and many logics, and it may not be true in all of them.
Yeah, so when you're working in some type theory, sort of meta-theoretic gold is normalization because that implies consistency. So, like, the biggest open problem in homotopy type theory solved by John Stirling last year with his thesis, probably the strongest thesis ever published in type theory, was proving normalization for cubical type theory. And how did he do that? Well, he asks the general question, which is actually related to what I'm doing in this talk. How does one prove any meta-theoretic property? And it turns out that the answer for him is Topos theory. So he has an entire thesis of Topos theory, and that's how you do meta theory nowadays. So now everyone has to pick up Sheaves and geometry and logic and just read it, because if you want to do meta theory, you need to know Topos theory.
Cubic type theory?
Cubical type theory.
So
Higher order type theory?
So it's a constructive model of univalence. So univalence usually is an axiom. In cubical type theory, univalence is not an axiom. It's a theorem. It also has normalization. Not normalization, it has that as well, but not canonicity. So every single closed term of Nat's type is a numeral. That's what Nat canonicity says. What does that mean? That means that if you have a function that produces a number, you can compute that number. So for example, let's suppose you have, like algebraic topology, you have a degree of a map, right? Degree is a number. Let's say you define your spaces, you define degree, and then you have degree is a number, right? In cubical type theory, it's impossible not to know a definite number. So you just make the program run and it will compute the degree of a map in like a commutative diagram, if you could define it.
Sorry, so back up a little. I think of homotopy type theory as things over a space, and there univalence is not necessarily true because spaces have holes in them and things like that.
Well, that's an interesting thing to say. For why univalence wouldn't be true because spaces have holes in them.
As opposed to complexes, which don't really have holes in them. Right. Okay, so now tell me what cubical spaces are, or cubical, what is that based on?
Cubical type theory is based on cubical sets with a confilling condition. So they do have confilling conditions. And the idea is basically, well, everything is a cofibration. So what is cofibration? Homotopy lifting property, right? So imagine like the bottom of a square, and then you provide homotopies on the two sides. So what cubical type theory is it gives you like a syntactic representation for the filler of that. And from that you can derive like the lid, and from that you can derive a syntactic representation for the filler. Now at the moment that's just a syntactic representation for this term is the lid of that. But then there are computation rules because if you evaluate at either boundary point, it reduces to whatever the top of the homotopy is. And so it turns out that you can make a system in which every single number that you define is an algorithm for computing that number. So it's a fully computational realization of univalent type theory based on the idea of cubical sets of confilling conditions.
I don't follow all of that, but let me just say something. Are cubical sets equivalent to complexes? Homotopically equivalent?
So you can have cubical sets and then you can impose a confilling condition on them. I am not 100% equipped to answer this question, so I know like the buzzwords and I know the concepts. And like I'm thinking about higher categories, Emily's my advisor, and then I'm thinking about like adding confilling conditions to like certain things, or I'm also thinking about doing it synthetically. So I don't have a direct answer to that.
There's a lot of different candidate definitions of cubical sets, including the one that this result was proved for. I think the one that this result was proved for is not exactly the same as what you get with simplicial sets. It's not wholly equivalent, otherwise you would just use simplicial sets.
Yeah.
There was a proposal that at some point, I don't know if they finished it yet, it was something like equivariant cubical or something would get you sort of a bit closer to an on-the-nose correspondence or embedding theorem. So it's a good model of spaces, but it's not exactly the same model of spaces.
Okay, well, one more question, then we'll
Yeah, of course.
just elaborate on what you said. I don't take it as an axiom, I take it as a theorem.
Right. So what that means is that you have like regular dependent type theory, and then you can sort of add a term to it called univalence axiom. It's a term that just witnesses the proof of univalence, but it has no computational behavior. So it's just something that you've added to the syntax and it doesn't have any behavior to it.
Right, but in certain models of homotopy type theory, that term is inhabited. In certain models, it's not inhabited, right?
Right, but the thing is, what if you have like a model, an initial model? What do I mean by initial model? That's the topic of this section. So lambda calculus isn't actually a syntax. It's actually a categorical universal property. That's what the theme is going to be. So how you choose the initial model in your structure category sort of matters. And it might have nicer properties. So the property of being fully computational means that, for example, any term that witnesses like is a number, a definite number, is an algorithm that can reduce with the rules of the theory to a number. That's not true of every single syntactic presentation, right? So the difference between an axiom and a theorem is that a theorem has computational behavior. That a theorem, when you add it to the system via like the structure of the thing, it has computational behavior and it has nice metatheoretic properties like NAT candidacy. What I call an axiom versus just a metatheoretic property that you can prove is that when you add an axiom, you lose metatheoretic properties like NAT canonicity. And in most versions of like book homotopy type theory, you do not have nice properties like NAT canonicity in the theory, because it's not something that just comes out of the theory. It's an axiom that you've inserted, and that axiom does tend to have good behavior. Does that make sense?
It makes sense, but I reserve the right to ask it at the end of the talk when you talk about the category.
Yeah, no, I'd be happy to talk about this a lot more. I can explain exactly like how I program in cubicle type theory. This all is formalized in cubicle type theory. So I do cubicle type theory on a computer. Okay, so what's the motivation? So like this is exactly what we were talking about before. So when we're implementing a programming language, so this is the story. 2 summers ago, I taught this course. It was Introduction to Proofs, Advanced Introduction to Proofs. I taught it like a type theory course. So the introductory proofs via type theory, they're never going to let me teach the course again, never. But
did the students appreciate it?
I had core followers.
You had?
Core followers.
Okay.
There was a group of 5 core followers, and they had the most productive summer of their lives.
Okay.
5 out of 14, but the core followers existed. And I followed some of them like after this, and they were doing really well for themselves in the course. So I defined substitution at one point. And which I didn't define before. I said we all intuitively understand substitution. But I'm using a source, and I found a mistake in the definition of substitution. I'm like, aha. So I'm presenting the correct definition. Then the next day I'm in a bath. And I realize, oh shit, I made another mistake in the definition of substitution. Then I'm presenting the second corrected version in class. And then a student asks me, can we ever know if our definition of substitution is correct? And I said that the notion of the correctness of a definition is tenuous. So you can sleep at night hoping that you've correctly defined substitution, but can you ever really know? Right? That's question 1. What's question 2? Well, that's exactly what you asked. When I wrote down substitution, did you ask me, is that a term constructor, right?
I did, yeah.
So you can make it a term constructor. If you make it a term constructor, that's explicit substitution. If If you don't make it explicit, that's explicit substitution. If you don't make it, then that's direct substitution, right? What about variables? Here I use letters for variables. What if my variables are numbers? De Bruijn variables, right? So all of these choices and how you define the language.
Probably need to charge.
Oh, I'm not plugged in. The cable must have fallen out. Thank you. That's a good catch. So all of these choices, they sort of lead to different languages. And so with all of these multiplicity, are we even talking about the same language? What connects all of these systems? What is simply typed lambda calculus? And so this problem actually has a solution. So it turns out that I was wrong. When I said you can't sleep at night knowing, I was wrong. You actually can. And the reason is that this was proven by Lemerick in 1980, but it had been known in folklore for 10 years prior. Here's a one-sentence definition of simply typed lambda calculus. Simply typed lambda calculus is a freely generated contextual Cartesian closed category. So now, what do you have to do? So
A freely generated contextual.
Cartesian
You are supposed to select
This is a
D
contextual.
something, not
well,
A something.
sure. It is any of the freely generated things.
Yeah.
The is a word that holds because it's unique to unique isomorphism. But I mean, it is just any of them, right? They're unique to unique isomorphism, but simply an implementation of simply typed lambda calculus is a freely generated contextual Cartesian closed
What
category.
does the contextual mean?
That's the entire topic of this section, and my main research contribution to this was the definition of a contextual category. So it turns out that categories on their own leads to a messier theory. There's a type theoretic version of categories known as contextual categories. I made this up. And it leads to a much better theory.
Okay, but the whole Lambeck and Scott
Yep.
is about this equivalence between a freely generated Cartesian closed category and a typed lambda.
Yeah, so the idea is that what is lambda calculus? Lambda calculus, you can sort of, when you have all of these syntactic rules, but then you ask what is the structure? And it has the structure of one of these mathematical objects. And sort of its initial in this class of mathematical objects. So how you think about it is that lambda calculus is you axiomatize a mathematical structure and then you ask, what are all of the theorems that I can prove in full generality about this mathematical structure? And sort of an initial object in the category of those structures, with like freely generated by something, is exactly a model that lets you witnesses syntactically exactly every single statement that can be proven generally and only those statements, right? So, okay, now what do I mean by you can sleep at night knowing the correctness of a definition of substitution? So I'm going to get into what contextual categories are, but we all know what a category is, right? So I can write down the definition of a category in a proof assistant, and I can stare at it, and I'm like, probably define category correctly, right? Okay, what else do I need? Cartesian close. Okay, a few lines, sure. Initial, I defined that, right? I haven't talked about substitution at all.
Wait, you just said you are going to define what a category is in a categorical language. Do you mean that, or?
I mean in a proof assistance. I've given the definition in type theory of a category. So
What's the language you are using to define?
that doesn't
what a-
matter.
Sure.
It doesn't matter. So the point is, if we believe that proof assistants actually verify the correctness of theorems, I can put all of these definitions in a proof assistance, and proof assistants, the idea is they're supposed to understand mathematics, at least at being able to verify the correctness of math. Then, if I have all of those definitions, I can prove that I have one of these, right? That doesn't refer to substitution at all, but in my construction I'll use substitution. But if I prove the theorem that I have an initial object, then I actually can sleep at night knowing that my definition of substitution is correct, provided that I define these words correctly, right? So that's amazing. This is like, you can actually know that you've defined substitution correctly, provided that you can be sure that you define category correctly in a proof assistance, and that's great. So, okay, that's the main point, and now I'm going to like define what this contextual, the notion of a contextual category is, right?
Just back up. What did Lambeck and Scott didn't know what contextual category theory, Cartesian category theory is?
So they didn't drop the word contextual. Contextual is my addition to the theory.
Right. So they have a definition of what a SLTC is.
Yeah, STLC would for them be a freely generated Cartesian closed category. Drop the word contextual.
Okay. And you're saying No, so you're giving another definition of an SLT.
So what's the idea? You axiomatize a mathematical structure and you ask what...
STLC.
STLC, yeah.
Yeah,
So
yeah,
the type of-
that's
It's a typo on the
a
slide.
Typo on the slide.
Oh, yeah, nice. Sorry, yeah, good catch.
Okay, but that's not, so you're giving, so Lambert and Scott gave one, and you're giving another one.
So I'm giving you the explanation for this.
Yeah, okay.
So you start off with a mathematical structure and you ask what are all the theorems that you can prove in it, right?
Mhm.
And then you have a syntax, and that's all the theorems you can prove in it. All of the theorems that you can prove of contextual Cartesian closed categories in full generality is the exact same set of theorems that you can prove of dropping the word contextual, of just Cartesian closed categories,
Okay.
right? There are two semantical worlds, and a simply typed lambda calculus is an initial object in both of these these semantical worlds. But you get a much better theory when you work with contextual categories. That's my idea.
Okay, so let's.
It's another presentation of Cartesian closed categories.
Yeah. So first off, we have to just discuss, like, what are we going to work with? So the idea behind a contextual category is that in categories we have types and morphisms as our primitive objects, right? In a category, in a contextual category, what did I say?
Morphisms.
Objects and morphisms are the primitive things in a category, right?
Right.
In a contextual category, our primitive objects are going to be types and terms. And from those primitive notions, we're going to derive the notions of objects and morphisms. But sort of objects and morphisms come from more primitive things, types and terms, and they're built up in the way that a type theory is built up. So in order to do this, we need to define several data structures in order to make this definition. The first definition is that of a context. Suppose that you have a collection of types. It's sort of confusing to say a type tie. But in type theory, our sets are actually types. So you have a type tie, right? What does it mean to be a context with respect to that notion of types? Well, it's just a list of types, right? So what do I mean by a list of types? Well, formally, that type of lists of types is an inductive type. It's generated by the empty list, and for every list of types and for every type, you get an extended context gamma plus A. So gamma would be a list of types, A would be a type, and then gamma plus A is another context, right? So I've just defined lists, type theoretically, right? So the takeaway from this is a context is a list of types, where we're starting with some primitive notion of types. Make sense?
Mhm.
Okay, our next construction is going to be the notion of an indexed list. Suppose that I have some family of elements parameterized by types, right? So from any family over types, I get a family over contexts. How do I get a family over contexts? Well, the idea is if I'm indexing it by a context, it should just be a list of elements of each type in the context, right? So it's similarly, it's called an index list. So there's an empty index list, that's indexed by the empty context. And if you have an index list indexed by gamma and an element T of A, then you can add that to the index list to get something indexed by gamma plus A. So index lists. Now, those are elements. Elements are indexed just by a type, right? But terms in lambda calculus are a bit different. Terms are indexed by a context and a type, right? So you have a term of type A in context gamma. So suppose that you have a notion of terms, which is anything that's indexed by a context and a type. Then we can basically construct a notion of terms, which is something indexed by two contexts. And terms, this notion, is known as substitutions. So a substitution is going to be something indexed by two contexts with respect to a notion of terms, which is something indexed by a context and a type. And the way that I define substitutions is that I just curry the argument gamma inside of term. So in other words, suppose I'm given something that's I have a notion of types, and then I have something that's indexed by a context and a type, right? Then I get something that's indexed by two contexts, just by having an index list of these terms. That's called a substitution. So basically, the morphisms in the category are going to be substitutions, but the primitive notion is going to be the terms. So terms, substitutions are built out of terms via index lists. Contexts are built out of types via lists. And we're going to build a categorical structure where the primitive notions are the terms and the
Isn't
types.
this very much like the vibration models that Seeley talks about, Robert Seeley?
I'm not sure about that, but I'm going to tell you a spoiler. I rediscovered Cartesian multi-categories.
So, yeah, my question was, how is this related to, you know, what Cartmel called contextual categories or
Right.
Trotsky's E-systems?
So that's why I actually can't use the word contextual category. These are simple contextual categories.
Okay.
In the case of simple type theory, that notion reduces to it, but contextual categories, like in full generality, are actually a notion for dependent type theory, and they're a bit more complex than this.
Okay, so so this really is the special case of Cartmel's contextual category.
I'm not 100% going to commit to that statement,
All right. But
morally speaking. They're equivalent.
it's almost the same.
Yeah, exactly.
Okay.
Can I go back to Lambeck and Scott, because that's the only thing
Sure.
I know in this world. It's because he taught it to me. To me, Lambeck and Scott says, if you take terms and you crunch them together as an equivalence class, then you get a category. Is that true?
So we are going to actually postulate some axioms. And the axioms are basically going to say that sort of the reduction rules have to hold within this type. So when we actually construct this, like in cubical type theory, we're going to construct it as a higher inductive type. So it's going to be a set with relations built into its very structure. So the terms are actually equivalence classes of terms, but what here says that they're not equivalence classes of terms, right? Here I just say that I have a notion of terms and a notion of types, right? Are they equivalence classes or not? You can actually construct a model in which they're not equivalence classes. You can construct a model in which terms are just normal forms, right?
You see, Nelson, what it seems to me like in Lambeck and Scott, they just talk about categories and type lambda calculus. But then Seeley says he replaces categories with vibrations, and now he talks about higher order type
I always thought
calculus.
the Seeley's thing was to get dependent type theory. That if you talk about slices, then you get dependent type.
Well, that's maybe
Yeah.
part of it, but
So, but he's not
This
talking
setup
about,
generalizes to dependent. That's part of the motivation.
oh, I don't know.
But
So this story is about simple type theory. Worked on extending these ideas to dependent type theory, and that led to my thesis project, which is not that. My thesis project is something else.
So wait a sec, there's two different things. There's polymorphism, higher type theory, and then dependent type theory. Aren't they different? There's not.
They're totally
They
different.
are.
They're not the
Yeah.
same. I mean,
Like in Martin-Loff type theory, you combine these two together, not in predicative polymorphism, you just have like a universe and that sort of match. Anyway, we can talk all about this all after the talk.
Right, no, it's getting
It's
late.
all
so
started
let's-
by Reynolds.
Yeah, so
Reynolds
I think we're
also
going
had
to-
these concepts. You know this guy Reynolds?
Yeah,
He also, John Reynolds, the late John Reynolds.
of course I know John Lawrence, yeah.
He also had this idea of like a context and so on, and he would talk about his interpretations in terms of context. It was all set theory and it's hard to read.
Anyway.
Hard to understand.
You can talk after.
Go.
Yeah. So, okay, so we have a way of building index lists and a way of building lists, and we need one final data structure, and that's variables. If you have a list of types, I want to prove that a type is inside that list of types, right? So how do I do that? I point by using either zero variables or successors, right? So ZV is a proof that A is a type in context gamma plus A. And then if I have a proof that A is a proof in context gamma, then I can sort of insert a B at the end of gamma, and that's the successor variable construction, right? So basically I'm going to use ZV and SV, and that's going to give me variables, and those are going to be proofs that types belong to a context, right? Now, a very surprising remark that I don't have time to go into in detail is that this is actually not a subtype of finite length n. This secretly looks like an equality type. These are actually going to be like if you don't have a set of types, if you have like a geometric space of type with higher homotopy groups, then variables are also going to have higher homotopy groups. I discovered this late into the project and I had to account for this. This was a bit annoying. This is why doing it in a proof assistant is good. You sort of think that variables are just these discrete index things, and it turns out that that definition looks like a Martin-Loff equality type. And you can't prove it, and then you realize, oh shit, they're not actually sets. So that's something that comes up. Now, variables can be used to index into indexed lists. So if you have a notion of elements indexed by a context, right, and then you have a proof that A is a type in gamma, then you can extract an element of type A from this else thing, right? And that's known as the function derive. So derive is going to be useful. So variables can index into an indexed lists. They're called index lists, so if you have an index, you can index them using Now, this section I'm just going to skip through very quickly. This isn't as important. I am actually going to just, because of for time issues. Variables look like a notion of terms in that they're indexed by a context and a type, right? So we can sort of consider a type theory in which the terms are variables, as so long as you have a notion of types. And the substitutions in this theory are known as renamings. And basically, renamings have the structure of a category. If you have a renaming and then you substitute into a variable, you just pick out a certain variable. You can define composition of two renamings from this, and then you can define weakening, and then you can construct the identity. So you have composition, you have identities, just variables on their own have the structure of a category. I'm not going to go into detail on this due to time, but the idea is, here I say they have the structure of a category. That's not good enough. They have finer structure than the structure of a category, and that's the structure of a contextual category. So what is a contextual category? So now I'm giving the definition of a simple contextual category. So a simple contextual category consists of the following. It has some data. First, it has a notion of types, right? From this, we derive a notion of context using our list constructor, right? So types are primitive, contexts are derived. Next off, we have a notion of terms. For every context and every type, we get a set or a type of terms. From this, we derive substitutions, index lists of terms, right? So types and terms are primitive, contexts and substitutions are derived. In the category structure, contexts and substitutions would be the objects and the morphisms, but they come from a more primitive thing. There off, we have
And substitution with composition?
So there's a bit of an annoying language barrier here, because there are object substitutions, which are a list of terms. And then there's also the operation of substituting. So there's a notion of substitution and a notion of substitutions. I couldn't find a better way to go about it. That's actually the standard. So our third ingredient is a notion of substitution. So given a term and given a substitution, you can substitute into the term. And that basically pulls back from context delta to context gamma. So it's like a pullback operator. You start with a term in context delta, you have a morphism from gamma to delta, then you get a term in context gamma. Now, from this notion of substitution, you can derive a notion of composition of substitutions by basically substituting into every single term in sigma. So, what are the primitive things? What are the primitive things in a category? Objects, morphisms, composition, right? Here, objects, morphisms, and composition come from a more primitive thing and are built up with the data structures that I described before, which is why I had to go into detail with what those data structures were. The data structures are like crucial to making this definition. And then finally, the last ingredient is we need identity substitutions. So for every context, there's an identity substitution, ID gamma in terms gamma gamma.
You need associativity.
Yeah, so then we need the axioms. So here are what the axioms are. The axioms are left and right identity laws, and notice that there's an asymmetry between the left and right identity laws. In the left identity law, it's a substitution on the left, so I'm using composition of substitutions. Whereas on the right identity law, I have a term and I'm substituting into it, so I'm using that notion. Why is there this asymmetry? I have a full explanation for that later.
Am I right? Is this right? I mean, when you say freely generated contextual, you mean what you're examining is what it's freely generated on.
Well, that's going to be the base types
Is that
later
the
on.
idea?
So freely generated is the
When they
last.
say freely generated Cartesian closed category, what do they mean? Freely generated on what?
Well, on
On a collection of objects.
On a set or
Yeah.
what?
No, you can do it on anything. It doesn't have to be a set. It can be a so if you mean like has higher homotopy structure or not, you can actually have higher
just
homotopy structure.
ordinary in Saunders McLean, if you look it up.
Yeah, so freely generate, that's going to come in
What do you
later.
mean? You mean on a set, right?
So this
To
is
me-
a tactic construction of
So, but-
freely generated.
So right now I'm not
Cartesian
defining
category.
freely
yeah.
generated. Right now I'm defining the word category with contextual
But
preface.
you're gonna use this context to
But-
freely generate.
But this is a freely
Ish.
generated. That's what I'm saying. This is the syntactic definition of a freely generated Cartesian closed category
Okay.
on a set of.
Yeah,
I think it's
types.
on a set of, with one element.
Well, no, this doesn't have to be one element. We're given
because-
any collection of base types. In
No,
this,
he's saying all base types.
She's saying,
She's saying all base types.
Well, I'll let.
Okay, so anyway, so
I'll
you
let
didn't
the
get it.
maestro
You're up to
continue.
the word category.
right, right.
And simple contextual category.
So then associativity is defined in terms of substitution into a term, and the right identity law is defined as a relationship substitution into a term. From these two things, we can derive the categorical versions of the right identity law and associativity, right? So as you said, we need the axioms in the category, so we throw these in, right? And then on the last thing, there's a technical assumption. Terms are as sets. What do I mean by this? Terms don't have higher homotopical structure. We can talk a lot after the lecture about whether this is necessary. It might not be necessary. But in this presentation, in my formalization, I assume that terms were as sets.
So the terms are freely generated, or the objects are freely generated. The types
Freely
are-
generated hasn't come in up to this point. You mentioned that like you can interpret this as a free construction, sure, but that's not what I mean at the moment. Freely generated is something else.
Okay.
In the way that I need it in the theory. Okay, so now this is just very quick. Like from this, you can define weakening. So we had identities, and the summary is that identities are a list of terms, right? An identity is a substitution, so it has components. What do we get from those components? Well, first off, it's a list, right? So we can take first and rest of the list. And so we get like the zero variable in the fundamental context projection from the identity. Using this, we can define weakening, which sort of takes a term in context gamma to a term in context gamma plus A. Or gamma plus B. And then we can sort of prove a substitution law for weakening. I'm just going to go over this very quickly. But weakenings aren't cool. Do you know what's cool? Variables. So we're going to pull apart each component of the identity and we're going to index it by variables, right? Then what you can prove, for example, is this law, that sort of, this is the variable that's is in components of the identity substitution that's indexed by a given variable. If you substitute into it, then it's like picking out a component. So it turns out this is why we had this asymmetry between the left and right identity laws. If we found the theory with variables instead of identities, then the left identity law is actually in terms of substitution. So the moral is that there's three ways to found this theory. One, you could assume that there is identity substitution. The other, you can assume that there are weakening operations. And the third, you can assume that there are variables. And these are three equivalent definitions. And with respect to the variable definition, this recovers the notion of a Cartesian multi-category. A Cartesian multi-category is presented as this usually is.
So stop. Just tell me what a category is. Bottom line.
Bottom line? So the catch is that variables, here's like a functoriality law for it. So variables look like they embed inside any category, but the problem is variables, they're not a set, because of what I mentioned before. So in homotopy type theory, a pre-category is a category in which the morphisms do not necessarily form a set. They can have higher homotopical structure. So that's why the word pre-category is used. A pre-category does not have more hom sets, it has hom types. But if you can actually prove that the hom types are sets, then you have a category.
Like a category enriched in top.
No, just a regular set theoretic category because your morphisms are a set.
No, the pre-category is like a category.
I can't say yes or no to that. I don't know what enriched in top means, and we're not going to get into it.
So you said can you just say again, you said there's three different
ways to found it. So in the way that I defined it originally, I assumed that there were identity substitutions, right?
Yeah.
You could also do it assuming that there are weakening operators. And you can also do it assuming there are variables.
Yeah, I'm trying to understand what you mean by variables, because it's a very specific notion of variables.
Yeah, so we have sort of the notion of variables that we used to describe before. They can be used to index into things.
Right.
So use those variables as a data structure to index into the identity and tear the identity apart into its components. Because the substitution is a list of terms. So each one of those terms, we're going to call them variables as well. So if you, instead of giving just the identity, you give each of the individual components of the identity, then you can found the entire theory. And then that looks like a Cartesian multi-category.
Okay, that's interesting.
So this is like a cool three-way presentation of the theory. This is my idea. And finally, okay, so now we need to give Cartesian closed, right? So what does it mean for one of these to be Cartesian closed? Now, the basic thing is that for every two types, we need to have an arrow type, right? So we have an operation on types, the arrow, right? Now, for every single term in context gamma plus A, you should be able to abstract it to a term in context gamma of type A arrow B, right? So this is, and then for application, I sort of do it the programmatical way. In the categorical way, we'd sort of have this adjunction and there would be an inverse to the adjunction. In the programmatical way, we don't like to think of it just as an inverse. We say that if you have a function and an argument, then you can apply the function to the argument, right? Now, it turns out that from that, using the following formula involving weakening, you can derive the categorical app, which is the inverse to lambda, which is the way category theorists will think of sort of the exponential adjunction, right?
Mm-hmm.
Now we need some properties. So subject to the following things. Lambda has to be natural, because the adjunction has to be a natural transformation, so we have naturality of lambda. And then we have the beta and the eta laws. So what are the beta and the eta laws? They exactly express that these two things are inverse. The categorical app operator and this is inverse, except for the beta law, we state it in a different way. We refer to it with the programmatical app operator, because that's closer to how we think of type theory as like a programming language.
Go.
Yep. So, okay, so that's what's, now I can say what is simply type lambda calculus. So we need one more notion. We need, if we have categories, we have to have functors, right? So what is a contextual functor, a functor between contextual categories? Well, it's not defined on objects and morphisms. It's defined by taking types to types and terms to terms, right? Mm-hmm. And from that, you derive an action on context and you derive an action on substitutions, right? So the definition, it's like not worth giving. If you just try to write down what the definition of functor should be with respect to this structure, you'd be able to do it in 10 minutes. Mm-hmm. So we have contextual functors. Now we actually need to talk about what we mean by freely generated, right? So if you just start with arrow types, you can't make anything in lambda calculus. You have to have a base type, right? You have to start with base types and then build them up with arrow types. So we're going to work similarly in the category not of just, I'm going to do it freely generated by a point in this talk, just for
One object.
One object.
What is that to?
In the talk I gave it with respect to one object. So we're no longer talking about just Cartesian closed contextual categories. We're now talking about pointed Cartesian closed contextual categories, right? So what is a freely generated by one object contextual Cartesian closed category? Well, it's an initial object in the category of pointed contextual Cartesian closed categories. So what is an implementation of STLC? It's an initial object in this pointed category. And the main results that I proved is this. Every single implementation of STLC admits a normalization theorem. And this is proved objectively. What does objectively mean? Objectively means that I didn't construct a syntactic model. I proved it using only the universal property for every single presentation of syntax. So where does this distinction between objective and subjective come from? Well, I mentioned John Sterling before. He coined that in his thesis. So it turns out that a math theorem can be subjective. And so what does it mean for a math theorem to be subjective? It's a proof about a specific initial object, a specific model of syntax. Whereas if you're proving it for just any initial object only using initiality, that's an objective meta theorem, not a subjective one, which deals with subjective presentations of initial objects. So I formalized in cubical agda an objective proof of the normalization theorem.
Nice.
Now this is 2/3 of my talk. Well, how are we for time? Because it's possible that we just won't have time for the third part.
Well, let's go ahead.
So I'm not going to show you how you do the objective proof, but I'm going to explain how you basically do a subjective proof. And this is the notion of normalization by evaluation. So it turns out that there's a very interesting way to do computation that does not involve reductions. It's possible to normalize a term without ever performing a single reduction.
Okay, you didn't define objective, you didn't define subjective, so I don't know what you're talking about.
Oh, sure, but this part of the talk is sort of like,
You don't have to divide.
What's
Is this
idea?
right, objective is a formal deduction, subjective is a proof in some model, in
So-
some particular model of something.
Is she saying that? Or is that?
It's
That's
a
my
bit
understanding.
different.
That's my
Um,
understanding, that's the model theory understanding.
sort of there is, yeah, that's a good idea.
No, so restate it now because I wasn't listening to him.
Sort of the thought is that objective and subjective are, did you prove things using only universal properties, or did you just construct an initial object and then use properties of that construction to prove the property about the initial object, right? So technically these approaches are equivalent, because if you prove something about a specific initial objects are equivalent to unique isomorphism, right? So by working with a specific initial object, you sort of proven something for every initial object in full generality. But you're not doing it the way category theory intends.
Well, I meant something simpler, I just meant an objective means a formal deduction of something that's true in every model
Yeah.
of the theory. Subjective is a proof of something in some particular model.
Which may happen
No,
to be the
no,
initial model.
because that's not actually what's happening here, because it's still an initial object.
Well, I don't
A
care.
specific- yeah, sure.
Nothing to do with initial or anything like that, just
Yeah.
prove anything. In
Okay.
an argument in a
So
model.
that's a model theoretic.
Yeah, that's what I understand, the difference between.
Okay, but she said something different.
So
I
MDE.
like both of them. Go.
Yeah.
But anyway,
Indeed.
according to Levere, syntax is the model of some other syntax anyway, so.
So here I'm just going to define what we defined before at the start of the talk, simply type lambda calculus, a specific syntactic presentation. And I'll work with a specific syntactic presentation. So what are our types? There's a base type, it's freely generated by a point, and there are arrows, right? That's what we had before. But now I'm just writing out as an inductive
I
definition.
agree with.
Then we have terms. Terms are indexed by a context and a type. And these terms, it's actually a bit interesting, because I'm not doing it like I did it before. Before, what I did is I gave a context-free grammar, which means that context-free grammars just compose things from units of composition. They don't care about structure. This is actually a context-sensitive definition. Every single term that you can write down with respect to these rules is well-typed. You can't write down non-well-typed terms using these rules, because I sort of keep typing information while I write down this definition. But the point is we have variables, VV, lambdas, and application, APP. So this sort of gives me a syntax for lambda calculus. I haven't defined what composition is, right? I've just given you a syntax for terms. In fact, these terms wouldn't satisfy beta and eta laws because two different terms that reduce to one another aren't equivalent at the moment. But we're going to ignore that. We're just going to ignore that. We're going to imagine maybe I quotiented at some point later in time. I don't have to define it.
Quotient being equivalence clauses.
Exactly.
All right.
Which in cubic Lambda you can do using higher inductive types. We have a really good way of doing quotients. Oh, now here's code. So at a certain point in time, we're going to start counting lines of code. It's going to become relevant. The definition that I just gave can be given in code. So types, you'd say data type, base is a type, arrow is an operation. Terms, V is something that takes a variable to a term, lambda is something that abstracts over a variable in a term, an application takes a term of arrow type and a term of type A to return a term of type B. So anyway, we are going to look at some code at some points in time. Evaluation. What is evaluation? Well, now we know what evaluation is. We have syntax. Suppose that we actually have, suppose it's actually a quotient. Suppose we actually have a notion of substitution. Suppose that we prove that the thing before has the structure of an initial object, right? In this category. That would mean that we get a notion of evaluation. So in any other CCC category, contextual CCC category, we get an interpretation. And how is that interpretation specified? We need to specify which object the base type is sent to, or which type the base type is sent to, because it's a contextual category. So if we specify where the base type goes, then it turns out that that uniquely specifies a contextual functor. Arrows have to go to the arrow. Variables, because it's a contextual functors have to preserve variables, have to go to variables. Lambdas have to go to lambdas, application has to go to application. So what is evaluation? Evaluation is just interpreting syntax inside of semantics. That's the idea.
So you're getting a functor now between
From syntax, a contextual functor from syntax into any other contextual Cartesian closed category. And that functor is uniquely determined by where I send the base type. Okay, what's a great Cartesian closed category? Sets. Sets, right? So what is that arrow in sets? It's going to be functions, right? So elements, it takes a type to basically the sets that corresponds to that type. So the base type is sent to some set x, where x is going to be an uninterpreted base type. I'm not going to say what base is sent to, it's just going to be sent to a whole x, right? So this is like an arbitrary notion of evaluation. I can sort of put a whole and not define something, and then it can check the rest of it according to that. Arrows get sent to function types, right? And sort of, then what is evaluation? Evaluation takes a term of type A in context gamma to a map from lists of elements of type gamma to an element of type A. Sort of, if you work out the theory, that's what it should be. And if you work out what the notion of evaluation is by understanding what the Cartesian closed structure is on sets, and by understanding just what the definitions are, you get this notion of evaluation. And again, for time, I'm not going to go into this, but basically this follows just directly from the definitions that I gave before, if we understand what the Cartesian closed structure is in. So like, these rules would follow from what is lambda, what is application, what is the beta and eta laws inside of sets. Well, not beta and eta, but lambda and application.
Of the type of eval, does the curly bracket mean anything?
Yes, the curly brackets mean that technically I need to specify a context and a type and then a term, right? But if I give a term, maybe I can infer what the context and the type are, right? So what this says is that these are implicit arguments. So I'm going to exclude them from my formulas when I apply, and I'm going to say they can be inferred from giving the term, right? And then when I'm given this definition, I'm only giving the term. I'm not giving gamma and A. That's what the brackets are. Great question.
So it's like just I can interpret it as there are two more parameters.
Except syntactically, when you apply, yes, there are secretly two more parameters, but they don't appear here. Now, sort of, okay, this is like, we talked about 2 and plus, right? This is a wall of text, but we talked about how lambda terms can represent 2 plus 2, right? So this is plus, this is 2. What is the church type? What is the type of numbers anyway? The type of numbers is A implies A in parentheses implies A implies A. That's sort of a type that represents what church numerals are. And we can talk a lot about Reynolds and whether every single numeral is that. That's parametricity.
Well, I think Reynolds was a student of church, if I'm not mistaken. Was he not?
I don't recall.
Well, let me check.
Now, sort of, here's like the shocking thing. I can evaluate some, which means that it's going to be turned into a set theoretic function, right? And I can just put this in my proof assistant, right? I can check what is the type of evaluation sum. Well, it's going to be a set theoretic function from elements of the empty context, which is just nothing, to x to x to x to x, where this is the uninterpreted type from before. And then I normalize it, and it normalizes to this. So basically, the secret is that in like the computer, the functions, it has a theory of functions, and those functions can be normalized. So as a function, it's actually going to this normal form. That's me just hijacking the normalization inside of semantics, right? But it sort of morally looks like we almost get normalization just by interpreting in sets and doing nothing else, right? So the question is, can we leverage this to get a normal form out of it? Can we return back to syntax from that function? And how you think about this is that sort of by interpreting something inside functions, you're sort of compiling to a function, right? So the question is basically, can we decompile? Can we decompile a function into a source expression in lambda calculus? And that's really the trick for normalization by evaluation. And so in order to talk about it, we have to talk about normals and neutrals. So we basically want to define a type of normal forms, which are expressions that do not have lambdas applied to expressions, because that reduces, right? So we want to define what the normal forms are. Well, it turns out that you can't just define the normal forms inductively. Why? Because some normal forms are lambdas, right? There are normal forms that are lambdas. Well, if you apply a lambda onto something, it's no longer a normal form, right? So normal forms can't just be defined as inductively biasing grammar. So it turns out that you have to have an auxiliary definition of neutral terms. What are neutral terms? Neutral terms are something that you can apply things to and be guaranteed that no computation happens. Well, what's an example of a neutral term? A variable. If you take a variable, which is a term of function type, and you apply anything to it, it can't reduce because it's a variable, it's not a lambda, right? But that expression itself, a variable of something applied to it, is also neutral because it's still maximally blocked off from computation. So what a neutral form is it's either a variable or a variable with several normal forms applied to it. Where I haven't defined normal forms, but these are two mutually inductive definitions. So basically, neutrals are like variables, or variables with several things applied to them, right? And they're important in the auxiliary definition of normal forms. Now, sort of, we want eta expansion, because the eta rule is also in play. And in order to ensure eta expansion, what we're going to say is that neutral terms are normal forms only at the base type. We're only going to allow embedding neutrals as new normals at the base type. But there's like a trick where you sort of do like the categorical APP operator, which is defined on neutral terms, and then sort of that pulls out all of the things into the context, and then eventually you'll get down to the base type by stripping away all of the arrows, and then you can embed, and then you can abstract. So that ensures eta expansion. Anyway, for anyone who's not an expert in what that means, that's not that relevant. For a technical reason, we will allow neutrals to bend normals at the base type. And then application, or lambda rather, is a normal form constructor, right? So now we've defined what our normal forms are, auxiliary with respect to neutral terms. And the idea is that the normal forms are going to be expressions in which there is no reducible expressions. So that's how you get normal forms. And what we want is to, from a lambda term, to produce a normal form. Right?
I just want to say, don't answer now, but at the end of this talk, I'm going to ask you to talk about church roster.
Sure, yeah, I can talk about that.
Because it looks related, no?
So in normal and neutral forms, there sort of isn't any reduction because there can't be any reduction that applies to it. Church roster is something that applies when you have reduction, you're talking about confluence of reduction, right?
Right.
But in here, this is specifically defined so there can't be any reduction in anything that you write down in this grammar.
But you can think of church roster as, if there is a reduction, it's unique.
Sure, and it terminates in this. So we've specified what the terminating points of the reduction are. Church roster, by the way, can hold without normalization. You can have confluent reduction that's non-normalizing. Anyway, okay, so here's how we define it in AGDA. Neutrals, neutral variables, application, embedding of neutrals, and lambdas, right? Okay, so pretty quick ACT code. That's the definition. Okay, so how are we going to normalize? Well, all that we know about is evaluation in sets at the moment. I've talked about semantics as sets, theoretic semantics, right? So we're going to make a mistake. Terms are terms in a context. So a term of type A in a context gamma. You know what? Let's forget about the context. Let's say there's just a set of terms of type A. And contexts don't matter, right? At all. So we're just going to imagine that we have sets. So now if you have a term, normal form, let's say, of type A, and let's say M is a neutral of type A or B, and N is a normal of type A. Then you can form the application, irrespective of what context these live in. We're going to forget about context. You can just apply anything, any neutral of arrow type onto a normal, forgetting about context, right? So we're going to try and do this all in sets. And then we're going to realize that we need to think about context. And that's where we're going to go to presheaves. Except none of us know what presheaves are. So we're going to make a mistake and rediscover the definition of presheaves. And that's basically what happens in this section of the talk. Now, what do we basically need to say in order to get an interpretation? We need to say what set the base type goes to, right? So the base type is going to be sent to the set of normal forms in base type. And that uniquely specifies an interpretation of simply typed lambda calculus into sets, right? So what's the interpretation of a context? An interpretation of a context is it's basically an index list from the sets. You sort of, maybe you can say take the Cartesian products of the sets, although I wouldn't form the Cartesian product, I'd form a data structure which is an index list constructor because we have that and it's great. So the interpretation of a term is that it gives you a morphism. So if you have an interpretation of a type A, the elements of that set are going to be known as the semantic elements of type A, right? So any element of the set, semantics of A is a semantic element of type A. So the interpretation of a term is as a function from semantic elements in gamma to semantic elements in A. And now, how do we get normal forms out of it? Well, if that's our interpretation of syntax, then in order to get a normal form, we need a way to sort of decompile semantic elements into syntax, right? And that's going to be known as quote. Quote is a decompiling mechanism that turns semantic expressions into normal forms, right? And unquote is going to be the reverse of that. It's going to be a compiler mechanism. It's going to turn syntax into semantic elements.
Quotes.
Sorry, I said that wrong. Neutrals in semantic elements. And sorry, go ahead.
So the reason why quote exists is because you're going to the normal form. There's only one. Usually there are many different syntactical ways of describing one semantical thing.
So at the moment, this is just a function. There's nothing in this signature that says that it's the normal form of that semantic element, right? However, you can sort of, a normal form is sort of like a very discrete thing, right? So that's like actual code. So we're sort of turning like maybe a function that can be defined by many formulas set theoretically into a piece of code. We're turning a extensional function into an intensional definition. And that's really interesting, right?
Well, I mean, in the construction of normal form itself, it was set up or called to not allow reduction, right? It's already reduction free by construction, so that eliminates the possible other versions of it.
So there's only one normal.
So for like a natural or something, there's only one normal form because you know it's red X free. It's free of reducible expressions by definition.
Okay, good.
So what is quote? Quote takes a semantic element to a normal form. Unquote takes a neutral to a semantic element. Why neutrals? We'll get to it in a moment. The domain has to be neutrals. So how do we define these? That's the question. Well, it turns out that we're going to define them by induction on what the type is. So it's going to be structurally inductive on the type. What is unquote? Well, unquote is going to be the easier case. It takes a neutral term to a semantic element, right? So let's think about what are the semantic elements at base type? Well, we defined the interpretation such that at base type, the semantic elements are just the normal forms, right? Now we have, how do we take a neutral to a normal? At base type, there's an embedding, right? So at the base type, unquote just takes a neutral and turns it into a normal via this neutral constructor, right? Now at arrow type, it's interesting. Because at arrow type, a neutral of type A to B is supposed to be interpreted as a function of semantic elements of type A to semantic elements of type B, right? So what are we given? We're given a semantic element of type A and we're given a neutral of type A arrow B, right? So now what do? Well, we take that semantic element and quote is being defined by recursion on the type, right? Mutually with unquote. So we have access to quote and unquote at the types A and B. So what we do is we take the semantic element and we decompile it to a piece of syntax using quote at the type A. Then we can form the application.
Right.
And this is why it has to be the domain of neutral terms. Because in an application, this term has to be neutral. That's why the domain of unquote is neutral terms, right? And now we have a neutral term of type B, right? And now we can compile that because we can recursively access quote and unquote at types A and B, and now we get a semantic element. Okay, so that's unquote, assuming that we have quote defined as well recursively at simpler types. How do we find quote? Now quote is really, really interesting because quote, that's a decompiler. It turns semantics into syntax. So how do you pull syntax out of semantics? Well, okay, let's think about it. We're going to define it recursively on the type. So at the base type, we're given a normal form, and we're supposed to produce, we're given a semantic element, which is a normal form, right? And we're supposed to produce a normal form, right? So it's just the identity at the base type. Now, what about at arrow types? At arrow types, we're given a semantic element of type arrow B, which means a function from semantic elements of type A to semantic elements of type B, right? So if we had a semantic element of type A, then we could use this function to get a semantic element of type B, right? Then we could recursively decompile that to get a semantic element, to get a normal form of type B, right? And then we could abstract to get a normal form of type A arrow B. Now the question is, where are we going to pull a semantic element of type A from thin air? Well, remember, we're not thinking about contexts. So why not just compile a variable? Suppose the variable has type A. We're going to compile it. Then we're going to take that sort of semantic compilation of a variable. We're going to plug it into this semantic function. We're going to get a semantic element of type B. We're going to decompile it, and then we're going to abstract to get a normal form of type A arrow B. So this is like a swindle. We're pulling a variable, a semantic element of type A from thin air by using a variable. And in order to justify this, we're going to need to talk about context and how contexts play in all of this, right? But suppose we don't care about context. Then if I locked you in a room for 25 minutes, you'd be able to write down both of these definitions in a mutually recursive way. Sort of, it turns out that if you're doing it by recursion on types, there's only one way to write it down, right? You sort of have no choices here. So bam, we have a compiler and a decompiler, right? So now how do we get a normalization algorithm from this? Well, quote, so the interpretation of a term is that it takes semantic elements in context gamma to semantic elements of type A. Quote, takes semantic elements to normal forms. Unquote, takes neutrals to semantic elements. So what do? First off, we need to cook up a bunch of semantic elements in context gamma. How are we going to do that? Well, what we're going to do is we're going to unquote a bunch of variables. Now, we could technically take the same variable over and over again if we don't care about context, but when we think about context, really we're going to take the identity variables, the identity substitution from gamma to gamma. Those variables. We're going to unquote them. That gives us a bunch of semantic elements of type gamma. We're going to put that into the machine that we compiled from the term. And then we're going to get a semantic element of type A, and then we're going to decompile that. And that gives us a normal form. So, bam, we have a normalization algorithm, assuming that we don't have to care about contexts. Now, what's so cool about this? We've just normalized without ever performing reduction. How you're thinking about it, Church roster, is that you perform one reduction step, another reduction step, another reduction step, until you get to a normal form, right? Wherever did we talk about reduction here? We didn't. We wrote a compiler and decompiler.
So you take any term and you unquote and then quote or quote?
So the term gets interpreted in semantics, which gives a function, right? Then what we do is, if we have this function, the idea is we need to cook up a bunch of semantic elements of type gamma, right? Then if we cook up a bunch of semantic elements of type gamma, we get a semantic element of type A, right? And if we have a semantic element of type A, we can decompile it to a normal form, right? So how do we cook them up? The cooking them up is unquoting variables, right? So we unquote a bunch of variables to get semantic elements of type gamma. We plug it into the interpretation of T to get a semantic element of type A, and then we quote it, decompile it into a normal form. This is magic. This is like, you can write this definition on your own, but like, how is this doing normalization, right? Like, there's no reduction. This is reduction-free normalization, and that's the idea of normalization by evaluation.
Well, you said swindle, and then the swindle is in a sense that that there's a substitution machinery secretly built into set theory.
So how was this discovered, by the way? This was discovered because someone thought, how do I write a normalization algorithm? Well, what if I just interpret my lambda terms as Lisp lambdas?
Right.
And then leverage the implementation of Lisp to normalize. Well, secretly what we're doing is that we can compute set theoretic functions. The idea of we can compute set theoretic functions, we're leveraging the normalization machinery of set theory in order to do this. That's the catch.
This is fascinating. So I want you to finish before we, no more questions. Until you win.
Right. So the rest of the talk is basically, it's going to take like 15 to 20 minutes more, which is how we account for context. Although I can go through this very quickly. So we don't know what pre-sheaves are. We're not going to say that we're going to interpret it in pre-sheaves. We're going to say that we're going to interpret it in context-indexed set families, right? So instead of just sets, there's sets that are indexed by context, right? I don't know what a pre-sheaf is.
Good. Thank you.
Okay. So what's the interpretation of a type A then? Well, it's a context index set family, which means that for every context gamma, we get a set, right? Now, what's the interpretation then at base type? At base type, we're going to take the set at gamma to be normal forms of base type in context gamma, right? So now we're accounting for context, right? So I specified which context index set family the base type goes to. And that gives an interpretation for every single type, right? Now, what is it for arrow types? Well, I don't know what the pre-sheaf exponential is. I'm just going to do it very naively. At arrow type, at section gamma, it's going to be the set of functions from elements of A and gamma to elements of B and gamma, right?
Uh-oh.
So everyone who knows what the pre-sheaf exponential is knows why this goes wrong. But for now, we don't know what the pre-sheaf exponential is. We're just going to do this, right? Naively, right? So then what are quote and unquote supposed to be? Quote and unquote are refined to also be indexed by a context, and that context stays fixed, right?
The problem is functoriality. The problem is one is covariant and one is contravariant in some sense.
Well, everything is contravariant in the context. We're going to see that elements are contravariant in the context and that normal forms and neutral forms are contravariant in the context as well. So, okay, when I said swindle before, what was the real swindle? The real swindle, as I refer to it, was this problem that we were unquoting a variable, right? Now, that variable of type A, where does it naturally live? It naturally lives in context gamma plus A, right? But the problem is that if we're sort of quoting a term f at gamma, then f is a function from semantic elements of type A and gamma to semantic elements of type B and gamma, right? But if I quote this variable, then I'm doing it at type gamma plus A. So it's actually a semantic element in context gamma plus A, right? So I can't apply f to it, which is what I would have wanted to do, right? So the problem is that there is a generalized, more strong context here.
Right.
And so what we really need is we need a semantic element to not just act on context gamma, but to act on any stronger context. How do we get this idea into our heads? Well, so the question is, where would that element f arise from in the first place? Suppose that it arises from unquoting something.
Sorry.
Suppose that it arises from unquoting something. So if we're unquoting a neutral m, then that gives us a semantic element function, and it would sort of take a semantic element s in of type A in context gamma, right? And then we try and then we think about this formula. That's the formula we came to before, right? So we decompile that semantic element, we apply it, and then we unquote it. Now the problem is that in this formula, we'd like to adjust it. The semantic element s that we're giving no longer lives in context gamma. It now lives in a more general context delta, right? So that's the hypothesis. How do I account for this situation? Well, this is where we realize they're not just context index set families. There's actually an action of renamings on these context index set families. So if I have, for example, a neutral in type context gamma and I have a stronger context delta, then I should be able to pull back the neutral to context delta, right? So now we realize that actually, we actually need an action on normals and neutrals. So if you have a normal or a neutral and a renaming, then you can pull back from gamma to delta. By the way, before in AGDA I gave the definition of syntax and I gave the definition of normals and neutrals. We start counting now. We are going to start counting lines of code now. This is where the line of code's card count starts. Okay, so this is the action of renamings on normals and neutrals. We can define it in a mutually inductive way, great. right? So normals and neutrals are appreciated on the category of renamings. Not yet. We don't know what appreciative is yet. Okay, so how do we adjust this? Now if we have this action on renamings, and we're given an element S in a more general context, what does it mean in a more general context? It means that there's a renaming from delta to gamma, right? So if you're given this renaming from delta to gamma, and you're given this semantic element, then what you're going to do is you're going to sort of decompile that semantic element to type delta, because that's the only type you can decompile it at. And when you form the application, before applying it to M, you're going to pull back M from gamma to delta, right? And so that gives you a definition of unquote that works on any more general elements, on semantic elements in any more general context. So this is where we realize that we made a mistake, because we didn't actually do the pre-sheaf exponential. We just did the naive arrow type from gamma to delta. Sorry, from elements of type A and gamma to elements of type B and gamma. We actually need to change the definition of our elements, what the interpretation of an arrow type is as a context index set family, to not just be function of elements of type A and gamma to elements of type B and gamma, but elements of type A and delta to elements of type B and delta in any more general context, right? So we're strengthening our exponential. So bam, we just rediscovered the pre-sheaf exponential, great. And I'll explain where this comes from at the end. There's like a calculation. But like in the category theory seminar, you probably have seen the calculation of the pre-sheaf exponential, right? So, okay, now quote and unquote. Basically, we already talked about it. Unquote, we decompile S, we pull back M, and then we compile. Sorry, and that's the definition before. Now, if we sort of think about quote, the problem was that this variable lived in context gamma plus A, right? Which is a stronger context than gamma. What's the renaming that relates gamma plus A to gamma? Well, it's basically the fundamental context projection pi renaming, right? So we just have to throw that in. And basically with those two corrections, the definitions of quote and unquote go through, right? So now we have quote and unquote on. Well, okay, we can genuinely call them pre-sheaves now. Now, what's the last remaining thing? And we're almost done. Well, first off, what's going to be the interpretation of a term? Well, it's going to be similar to before, where we're sort of going to take the Cartesian product of these things. We're going to use our index list constructor. So the interpretation of a term T is that it's a delta index family of morphisms from elements of gamma in context delta to elements of A in context delta. That's just basically where the interpretation comes from. Now there's one final detail that we have to address. In order to define the interpretation of syntax into semantics, let's consider the case of lambda. In the case of lambda, suppose we have, we're trying to do this in context gamma, right? So, so we're going to consider any more general context delta than gamma. And we're going to give elements in delta, right? And now the thing is that we want to produce a semantic element of type A arrow B, which is going to be a function of semantic elements of type A to B, but in any more general context. So we generalize the context again to sigma. And we'd like to sort of put that semantic element S together with these semantic elements, but they live in different contexts. So what we realize is that elements themselves, these semantic elements, they also have to be a pre-sheaf. So we need to define what the action of renamings is on semantic elements, right? And so we're able to do that. 3 more lines of code, right? And then finally, with all of this together, we're able to define evaluation. And this definition of evaluation, if you compare it with the set theoretic one, is basically the same. There are just like a handful of syntactic differences, but it's almost the same definition. We have to sort of use this pulling back on else to sort of make this happen, but we do make it happen. So we get evaluation. And finally, we get normalization, right? Line of code count stops here. 26 lines of code.
Congratulations on refuting the de Bruijn ratio.
Yeah, sure. De Bruijn ratio. So that the de Bruijn ratio is the idea that if you have like mathematics on paper, the formalized mathematics is like much longer than it, right? 26 lines of code. That's the entire normalization by evaluation algorithm. And so my basically last slide is just like testing it out. We're going to define an embedding of normals and neutrals into syntax, right? and then we're going to take our example 2 plus 2 from before, and we're going to normalize it, and we're going to return to syntax. And these slides, when I compiled them, this code was type checked.
Nice.
So the normal form of 2 plus 2 is, this is the church numeral 4, proof reflexivity checked by a computer. And so that's the end of my talk, but I'm just going to say one more thing. So the idea is that, how do you actually prove normalization? Well, instead of doing pre-sheaves, you do a structured category, where essentially the structure of that category is that it contains normalization proofs. So it's a more complex category with a bunch of natural transformations, but it sort of builds up a normalization proof. And use this normalization by evaluation machinery to inductively build up a normalization proof. And so I formalized all of that, great. But you know what? You know what my goal was in all of this? It was to get a proof of 2 plus 2 equals 4. I wanted to get a normal form of proof that 2 plus 2 equals 4. And so I ran it, and it didn't normalize in half an hour. I was really sad. So then I realized I was using cubical agda, and there were some problems. Cubical agda was using higher inductive types. January of last year, I sat down, I rewrote everything using setoids and equivalence relations, and it was horrible. But I wrote it in the most minimal way, and then I got a thing where it was setoids of computational traces. So it would be in terms of beta and eta laws, right? That was basically my quality type, setoids of computational traces. Then I normalized it, and it normalized in a flash. So what I got was a proof that 2 plus 2 equals 4.
Well, Whitehead and Russell spent about 200 pages to get that.
And so here is the proof that 2 plus 2 equals 4.
Nice.
It's the proof that comes from category theory. Remember when I said we counted steps and it was 6 steps? If you use the category theory proof, it's this.
That's mathematical.
But what's sort of the most amazing thing from this? The idea for most people is that normalization by evaluation is supposed to be the antithesis of stepping, which is a computational trace. Here, I have used normalization by evaluation to produce a computational trace, and I call this stepping by evaluation. No one's done this before. Okay, and that's my talk.
Yeah, that's very cool.
And there's one comment about the pre-shift exponential. You didn't show the full.
Oh yeah, so let me show you that. Great, thanks for
No, the comment is that you said the naive one doesn't work because of functionality. It is right. Because you need functionality not only on the x and y, those two pre-sheaves, but also the c. Like when you treat them as when you treat the exponential as a functor, and then you plug in an object in the site.
Right.
Not the site, the source category. You need that variable to be functorial as well.
So how do we calculate this pre-sheaf exponential? What's with the section of pre-sheaf exponential at a given set x? Yaneda says that that's natural transformation from hx to f arrow g. The exponential says that this is hx times f, natural transformations to g. Pre-sheaf exponential. You rediscovered it. You just rediscover it when doing the normalization by evaluation algorithm. It's great.
Anyways, thank you very much.
Yeah.
Well, I don't have a comment. I have a request that when you finish your thesis, you come and give us a talk.
Awesome. I'd love to. I'm doing really interesting stuff. The thesis is more interesting than this, actually. But
Dependent type theory is more interesting.
yeah.
Anyways, very
Yeah,
much.
if you think about that naive one, it's not functorial in the x there.
Yeah, I did a.
I'm gonna stop the
less
recording because I
formal
want to.
version of